So today, I want to show you something that's going to make writing these electron configurations a little bit easier. Wouldn't it be nice to know ahead of time where you had to stop? And not have to keep track of every single electron and keep counting and adding them up along the way? Wouldn't that be nice to know ahead of time? So, I did not pick random elements for today's Bell work question. Okay, so what do we get for the electron configuration for boron? Okay, well, boron was number 5, so it was 1s2, 2s2, 2p1. Aluminum was number 13, so 1s2, 2s2, 2p6, that's 10, 3s2 is 12, 3p1 is 13. They asked you to do gallium. Gallium was number 31. Oh, 1s2, 2s2, 2p6, 3s2. I can go really fast because I know I'm going to go to at least 3p6. Okay, 3p6 gives me 18. After 3p comes 4s. There's 20. Then comes 3d. That's 10. And then comes 4p1. Okay. Now, what do those configurations all have in common? They all end in p1. Look at where they're at on the periodic table. They're all in the same column. You think that's accidental? No, because the one after each one of these would be end in P2, right? So let me point out something nice about your periodic table. Okay. You notice the first section? The first section is 2 columns wide. Okay. That's because everything in the first ones, 2 columns wide, is where s orbitals are filling. Fact is, if you look at the electron configuration, hydrogen would be 1s1. Right? Helium would be 2s1, then 2s2, 1s2, got that backwards. Then 2s1, that would make that 2s2. And we already know that this one's going to end in 2p, right? Because we just did boron. That's going to be 2p1, so that's going to be in 2p2, 2p3, 2p4, 2p5, 2p6. Okay. That's where they're going to stop. So if you got one in the first column, it's going to stop it at S1. If you stop at the second column, it's going to end in S2. Then over here where it's 6 wide, the first column is going to end in P1, then P2, then P3, then P4, then P5, then P6. Okay. How wide is the green section on the periodic table? It's 10 elements wide, right? So which kind of orbitals hold 10? T. And you'll notice that right after 4s1 and 4s2, what comes? Right after 4s comes 3d. So this would be 3d1, 3d2, 3d3, 3d... nothing ever ends in 3d4, so that's going to be a 3d5, but I'm going to have that 4s1 before it. Right, because nothing ever ends in d4. Then there's 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. And what comes right after 3d is 4p. right? So see how the patterns in our electron configurations show up on the periodic table. Oh, you can't have D9. It should be D10 and S1. That's right. 4S1, 3D10. Right? You shouldn't have a D9. Okay, how many boxes do you think are in the bottom? 14, right? Everybody see why you should be able to guess that there's going to be 14? The f orbitals. Now, there is a slight trick here, though. The f orbitals are always off 1. Okay, so let's look and see where you go to the f orbitals. Okay, it's right here. So this would be 1, 2, 3, 4, 5, 6s1, right? And then it'd be 6s2. Now here's the problem. If you look at the numbers on your periodic table, right here is lanthanum number 57. Okay, the 57th electron, well, what comes after 6s? Is 4f. Okay, so there's a slight problem here, and they put it in the wrong place. This is really 4f1, and then 4f2, all the way through 4f14 here. And this is really 5d1. So I'll write that a little bigger. For F14 there, 5d1. So these two are off, or actually these two down here belong here. They belong here, and the ones at the end. The lanthanum and actinium begin at the beginning, should be at the beginning of Fs, and lutetium and lawrencium should be at the beginning of the Ds. So the Fs are 14 wide, but they're off by 1 on your periodic table. Okay, so this should make it easier, because if you can use this, you can know where to stop. So if I asked you to write the electron configuration for, say, something bizarre like platinum. Okay. So platinum's right here. So that is 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's 8 over. Platinum's right there. So that's going to be, I should know that platinum's going to end at D8. Right? And which D8? Well, if the first row is 3, 3D, 4D, 5D8. So I should keep going until I hit 5D8. So I don't have to count until I get there, as long as I follow those diagonals along the way. So that's going to save you some time. And it's a good way of checking. If you are counting, you can check to see that it shows up in the right place on the table. Because you should count at the end just to make sure, but the two should match each other. Does that make sense? How that's going to save you some time? If you know where to find it on the periodic table, it tells you where to stop on your electron configurations. The entire next unit is on the periodic table. We'll find a lot of patterns on the periodic table. Okay? So that's where I wanted to go. All right, so last topic. The physics of the very small. And every time we talk about curriculum with other people, they're surprised we teach quantum mechanics in chemistry. Because they say, oh, quantum mechanics is physics. I said, yeah, but I needed to explain chemistry. Chemistry is just applied physics after all. Okay? So quantum mechanics explains how the very small behaves. quantum, little chunks of energy, mechanics, how they work. So, and by very small, we mean atom-sized or smaller. Okay? Because we don't worry about the probability of where you are. We're pretty sure where you're at. Okay? But quantum mechanics is based on probability. We never say where the electron, if we say where the electron is, we're saying the wrong thing. I may say it where it is, but that is just a probability of where you could find it. This is where you have the best chance of finding it. I mean, if we were to take a map of this school and say, where would you find a student? You'd probably show lots of things in the classroom, good chance to find them in the classroom, small chance of finding them in the kitchen, smaller chance of finding them in the staff restroom. But why is quantum mechanics based on probability? Well, ultimately, when you get down to it, it's based on probability because of something called the Heisenberg uncertainty principle. And there are many aspects of Heisenberg's uncertainty principle. We're just going to talk about one of them. I may bring up another one along the way, but things at the quantum level are not exact. They're only based on probability. That's because we find out there's a limit to what we can know. There's a limit to what we can find out. Okay? And here is the Heisenberg uncertainty principle. It is impossible to know. Once a semester. It is impossible to know. Not hard, not difficult, not because you don't have enough information. It's impossible to know. Eat this. Both the position and speed of a particle. It's impossible to know both. I can know the speed, or I can know the position. I can't know both. Okay? The better we know one, the less we know about the other. If I know how fast it's going, I have no idea where it's at. If I know where it's at, I have no idea how it's moving. If that's the case, you're not going to be able to say where it is very well because it's going to move on you. And the limit comes out of a bizarre place. The reason why there's a limit is because by measuring the position, I change the speed. Or measuring the speed, I change the position. Measuring something changes the thing you're measuring and the thing you're measuring with. The act of measuring changes both the thing you're measuring and the thing you're measuring with. For example, if I were to take this ruler and lay it down on the table to measure how far it is across the table, what we don't see is a few of the atoms of the ruler are being rubbed off by the table. So the ruler is changing because the table's changing it. And a few of the atoms of the table are rubbing onto the ruler. And we can't see that every day, but I saw that kind of effect when I was working in a liquor store. And the liquor store I worked in was built in the 1900s at the University of Michigan. So it's a place everybody came in to get their coffee and donuts in the morning, okay? And sodas. Okay? So I was running the cash register there. But we had a problem when it rained. The problem was when it rained, there was a puddle right in front of the registers. Because for 80 years, people had been walking in that same place right in front of the register, and their feet had actually worn grooves into the cement. Okay? You don't think about your feet changing the ground you're walking on, but there's got to be a little bit of rubbing going off. Okay? I didn't recognize how it was there until I had to mop the floor, because you could actually see where they put their 2 feet. There was 2 little channels where people had walked their feet for years. So just walking on stuff changes it. Well, measuring it with a ruler changes it. Okay? There are lots of things like this. Speed and position are one of them. Okay? We don't see it measuring a desk very often. Okay? It's only going to be obvious when the things get really small. Because if I want to measure where an electron is, am I going to be able to use a ruler? Why can't I use a ruler to measure where the electron is? It's too big. So to measure where the electron is, I need something smaller than an electron. Are we okay with that? I've got to have something that's smaller than the electron, and the only thing smaller than an electron is light. Light, meaning not heavy, but light as the type of energy. That's the only thing that's smaller than electrons. There's a problem with this technique, though. I showed you, talked about the photoelectric effect. I showed you how black lights work. Light moves the electron around. So if I'm going to try to measure the electron with light, one of my problems is the light I shine moves the electron I'm trying to measure. And it actually is worse than that, because the light I measure with comes off a different color than it went in. If it interacts with the atom, I don't necessarily get the same color back. So the thing I'm measuring, where the electron is, that's hard to do because the electron gets moved around. The thing I'm measuring with, the light, hard to measure with because it changes as we're measuring. Okay. So here's the idea behind it. Oh, I clicked. Why didn't it go? I decided to freeze. Yeah. So if I'm going to hit a light wave onto a moving electron, okay, to tell its position, I can only tell it within one wave. I couldn't get any better. I can't figure out when it's halfway between waves. So the best I can do about where its location is within one wavelength of light. So if I make the wavelength, if I want to know where it's at, I need to make this wavelength short. And I want to make it a tiny wavelength if I want to measure where the electron's at, because electrons are tiny. But there's a problem with that. If I make the wavelength tiny, that means I made the frequency high, which means I made the energy high, so that when it hits that electron, it's going to knock it flying. So in figuring out where it's at by using a short wavelength, I knocked the electron flying and I have no idea how it was moving. Because the electron just goes flying off into space really fast because I hit it with a high energy wavelength. Okay? So if I know its position, I can't know how it's moving because I just hit it. Okay? On the opposite side, if I don't want to move it, the only way I can not move it is hit it with really low energy. And really low energy is a really long wave. Right? A really long wave. And really long waves have low energy, but that's, if I wanted to say where the electron was, the best I could do is how long that wave was. So the longer I make the wave, the better I'll know about how it's moving, because it'll be low energy, and I'll see what happens when the electron hits it. But I have no idea where it's at because it's someplace within that wave that's bigger than the atom it's in. So knowing one speed stops me from knowing the other position. And this one I can explain with mechanics, with a light. But the bizarre one is spin. Okay. So we talked about spin being a magnet going up and going down. So they take a stream of electrons that is 50-50, and they pass it by a magnet, and half of them have upspin and half of them have downspin. Okay? But if they take this one right here and pass it by another magnet, okay? They pass it by another magnet, and this magnet spin also has a left and a right. You spin left or spin right. And the electrons half spin left, half spin right. So I took the ones that spun up and down, I took the up ones, took care of it, I took those spike ones. Now, what's going to happen when I pass them by another magnet like the first one, where I'm testing up and down? Well, we tested here, it said they were up, right? I took the up and the right arrows. When you get here, half of them go up and half of them go down. Say, whoa. Because the act of measuring whether it's left or right stops you from knowing whether it's up or down. There's lots of quantum effects that are like that. The knowing one of them stops you from knowing the other. And the better you know one, the less you know about the other. If I pick the ones that had a 50% chance of going up, okay, then I would be better able to predict the percent that we're going to go up the second time. So if you push it by 2 ups at a time, it goes up and then up again. But if you do an up and then a right, you can't, the information about up disappears. Okay, which is kind of bizarre. And that's how quantum mechanics is, really bizarre. So Heisenberg uncertainty principle, we saw one part of it, speed and position. It shows lots of places that knowing one piece stops you from knowing the others. And then